Okay, hello, welcome to my channel. My name is Solo, and in this video, we're going to determine when Nigeria's population size will reach 600 million. Good. Okay, so in our previous video, we're going to try to determine how many phone numbers are possible in Nigeria. And we're able to get about 600 million phone numbers. And we say, okay, well, do we have up to 600 million Nigerians? And if we don't, then when will this population size, 600 million, be reached? Well, I'm not in any way saying that having 600 million Nigerians will definitely mean that we'll have 600 million phone numbers, because population size of Nigerians includes children. You don't expect children to have phone numbers, and in fact, some Nigerians have more than one phone number. So, of course, laying aside all those irregularities, we just want to know what we'll get out from here. Okay, so we have some initial data. So 2010, we had about 161 million Nigerians. In 2024, we have about 230 million Nigerians. Good. Okay, so we're going to use this initial data, okay, to try to get a mathematical equation that will give us the population size for any time, or maybe that will give us a time given a population size. So in this case, we will try to determine the time given 600 million. Good. In other words, when will this 600 million will be reached by Nigeria's population size? Okay. So we're going to be using a very simple mathematical model, which infers that a population size, okay, that is a rate at which a population size changes, is directly proportional to the population. Good. So you think about this. If you have more people, let's say occupying a place, okay, you have more activities going on there compared to when you have fewer number of people. Okay, and some of those activities will affect the population size, like migrations, right? Like that is immigration and immigration, or you think about death and birth. So we're going to see that the rate at which a population size changes is directly proportional to the population. And we're going to put that down using some mathematical notation, and this is it. So the rate at which a population size changes, we're going to use P to denote the population. And not just that, since the population size changes with time, so you can observe here, I'm going to say that this population depends on time, so I'm using little t to denote the time. Good. So the rate at which this population size changes is directly proportional to the population itself. Okay, so I'm not using the proportionality because I've included a constant, and this constant is the rate at which the population changes. And as you can see, the population increases, that is to say we have a growth. And that tells us that this R here has to be positive. Good. Okay, so we're going to determine that. But first of all, we have to solve this simple differential equation. But this is too easy. And in fact, you can do that. And when you solve that, you're going to get this. You're going to get that P of t is A times e to the R of t. Where this A is gotten from constant of, where this is as a result of the constant of integration. Okay, so the next thing I'm going to do is I'm going to take the population size at 2010 to be my initial population. That is to say, I'm going to denote it this way, that P naught is population size at 2010. So I'm taking 2010 to be my initial population size. Good. So we're going to take that to be 161 million. Okay. And then we're going to take P 2024 here. Well, since 2024 is 14 years after 2010, that means this is going to be denoted as P14. Good. Which is 230 million. Okay, that's nice. Good. Okay, so using these two facts, well, I'm going to start off with the first one. This P naught means when time is 0. So we're going to substitute P being 0 here into both sides of this equation and try to determine the value of A. Then we're going to use this one to try to determine the value of R as well. Okay, so let's observe what that will give us. Well, when t is 0, it means we're going to have P of 0, which is the P naught as I mentioned earlier, which is 161 million. Okay, so maybe let me just put down the million and full like that. Well, this will just be, well, A times this number raised to the power of, that is A times e to the power of R, okay? Then you put 0 in place of t. Well, that will break everything down to 1, leaving us with just A. So what that tells us is that the value of A is P naught, which is 161 million. Alright, like that. Good. So I'm going to rewrite this solution. Okay, I'm going to rewrite it using the fact that A is 161 million, and we're going to get this. We're going to get 161 million. Okay, then e to the power of, well, RT. Great. So I've written the solution to the population at any given time t using the fact that A is found as 161 million. Okay, the next thing we'll try to determine is the rate. Well, with this rate, we can now solve our problem. So how do we do that? Well, we're going to use the second data, which is the size as 2024, which is what we call P14. That is to say, when the time is 14 years. Good. I forgot to mention that T here is in years. Okay. So when P is 14, notice that when T is 14, notice that we have 230 million. So we say when the time is 14 years. All right. I'm just going to put 14 there. The population size is 230 million, which we have it to be this. But we're going to substitute 14 for T. So this is 161 million. Then we have e to the power of 14r. Well, the 14r is from TR, where T is 14. Good. Okay, the next thing we'll do is to divide both sides by 161 million. Just a way of trying to get r as the subject, or to find the value of r, which is the rate of growth. Good. Okay, so what we'll have to do is to divide both sides by 161 million. When we do that, well, we are going to have about 1.42. This is 1.42 857. Okay, this is e to the power of 14r. Good. Okay, so since we have some exponential terms, of course we are going to make use of some logarithm, and this is a natural exponential function, which means we're going to make use of natural logarithm function. So we take the natural logarithm of both sides, which means we're going to have natural logarithm of this and the natural logarithm of that. So let me put down the 14 arrow on the left hand side, and this will give us about 0.35667. Okay, that's nice. Great. The next thing we'll have to do, of course, is to divide both sides by 14. When we do that, we're going to have about 0.0254 as the rate. So this thing shows us this is the rate at which the population changes, and like we said earlier, it is a positive number. Good. So we're going to use this rate, putting it back into this equation right here, and then we can use that to get the population at any given time, or the time given a population. Good. That is to say, we're going to have our population to be P of T is the 161 million. Then e to the power of, well, RT, but we found the R as this. So maybe let me just say R is going to be a very large number than T. That is, it's not a large number, but it consumes a lot of space. 4767. Okay, great. So this right here is the equation that will help us know the population at any given time. So I'm going to clean some parts, and then we're going to continue from here. Okay, so from the last one, we're able to determine that the population size given any time t is this. Good. Okay, so going back to the question says, when will the population be 600 million? That is, it's the question of time. Good. So what we have to do is to say, okay, assuming the population is 600 million, when will this happen? In other words, what will be the value of t? Good. So we're going to substitute 600 million in place of p, and then try to determine the value of t, which will be in years. Okay, so you put that right here. That means we're going to have 600 million. Okay. All right. So we're going to divide both sides by 161 million, and then from there we're going to take natural logarithm of both sides, then divide both sides by 0.0254767 to be able to get the value of t. Good. So we divide 600 million by 161 million. We're going to get about 3.7267. So let's say 3.7267 is e to the power of 0.0254767 t. Okay, that's nice. The next one would be to take natural logarithm of both sides to be able to create this exponential base. Okay, well, what natural logarithm of 3.7267 is about 1.315523. Okay, so you can verify from this. That will be 0.0254767 t. What you may say why do I have to carry about this long decimal part? Well, I'm just trying to make the thing as accurate as possible, but it's not going to be, but at least let it be close enough. Okay, great. Then the next thing will be to divide both sides by this number to be able to get t. So let me put t on this side. Let me just write it out here. That t is, well, we divide this number by that. When we do that, we're going to get about 51.6363. Good. And this is to say t is about 51.6363 in years. Well, what does that mean? That means in about 51.6363 years, which maybe you can write it into months and days if you want. That will be 51 years. Okay, years in short. Well, 6363, 0.6363, you can multiply that by 12 to get months, which will be about 7 months. And then you will have some remainder, let me see. Yeah, you will have some remainder which will make up about 19 days. Good. Well, 51 years from when? Okay. Well, that will be, it's close to 52. You can say approximately 52 years. Well, since we used 2010 as our initial population, remember the P0, that means we're going to add 52 years to 2010, which will give us 2062. So this population size will be reached at 2062. That's approximately. That is to say, by 2062, 600 million Nigerians, that is the size, 600 million must have been crossed. But that is kind of scary. 600 million, that's like almost 3 times what we had today. But well, that is based on the assumption that the rate remains constant or maybe averages out as we move on. Anyway, thanks for watching. Please share this video with your friends and continue for my next video.